So, talking about historically modern physics, starting with 1887, I mean, there are a few events that lead up to this. One, for an example, is Maxwell's equations. Um, the other is Millikan's oil drop experiment that precede these dates, that certainly are important to what we believe from what we consider modern physics. But I wanted to start with the Michelson-Morley experiment in 1887, um, just as a place to get started from. So, like I said, there are other events that are before 1887 that certainly contribute to the idea of modern physics. Like I said, Millikan's oil drop is certainly one of those items. Maxwell combining the equations for electricity and magnetism, that is definitely something that's worth mentioning that precedes Michelson and Morley, which have a major effect on modern physics. The whole relative motion starts to come into being because of Maxwell. Anyway, starting off with Michelson and Morley. Michelson and Morley is one of the more famous early experiments in modern physics. Michelson and Morley develop a way, well, let me give you a little background information. Before 1887, we believed that all waves needed a medium for which it travels through. We talk about mediums, we talk about, well, sound. A sound wave has a medium in which it travels through. That medium is air, is water, is the ground that we stand on. All those can transmit sound waves. Excuse me. Allowing sound to travel through them. Okay? So we believe that all waves needed that medium, to the point where Michelson and Morley develop an experiment to test the medium in which light traveled through. Okay? And that medium was called the luminescent ether. Now, what we believed about the luminescent ether, and let me draw, see how much space I got over here. Okay. So, the idea of the Michelson-Morley experiment is that we know that the Earth is revolving around the sun. So it's rotating around the sun. Okay? We also know that it rotates about its own axis. So as it's in motion, traveling through space, traveling through this luminescent ether, it's pushing through that medium. Okay? So as it's pushing through that medium, much in the same way as a boat pushes through the water, you get a buildup on the side in which it's traveling of this luminescent ether. So it's going to be thicker on this side, and it's going to be thinner, like in a wake of a boat, on that side. Okay? So thicker luminescent ether, thinner luminescent ether, and what we know about wave phenomenon is this more dense material will allow waves to travel faster. Okay? So the belief was that light would travel faster at the beginning of that, in that section where the ether was thicker. So here's my velocity vector at the beginning of it. And then when it travels through the wake of it, it would travel much slower. Okay? So from there, we come up with an experiment that requires a beam of light, a monochromic light. We call it monochromic because we're not talking about lasers, we're just talking about light of one frequency. To travel, so I have a beam of light coming out. It strikes a beam splitter, which allows part of the beam to travel, just keep going straight. Another part then is sent off in another direction. So it's the same beam of light, but part of it goes up and part of it goes off in this direction. Well, that one that goes off in other directions is then bounced off a series of mirrors, comes back, and then is recombined with that light. Okay? Now, the way in which this apparatus is set up is this distance is equal to the speed of light. Well, let me change that. That's not what I mean. This distance is equal to a multiple of the wavelengths. So think of this as a wavelength of 1 meter. Okay? So this distance would be 3 meters that it would have to travel. So it would travel a full 3 wavelengths before being recombined over at this point. Okay? So when it returns, it's going to be in the same phase, which means that the wave is going to look identical. So when I add them together, I get constructive interference, and the light looks normal. Okay? If, for some reason, light travels faster in these directions, because it's got thicker luminescent ether, then it's not going to travel one full wave. It's not going to travel 3 wavelengths. It may only travel 2.5 wavelengths. It's going faster. So instead of going 1 wave, 2 wave, 3 waves, oh, not quite 1 wave, not quite another wave, not quite another wave. So it doesn't do the full amount of waves. So instead of 3 wavelengths, it may be doing 2.5 or 2 3/4 or something along those lines. Well, if that happens, you get destructive interference, and you end up getting a pattern over here when the light strikes of destructive interference. Okay? They're interfering with themselves. So the experiment is set up so that if light travels faster through this space and this space, because of more luminescent ether, then you get an interference pattern. If it doesn't and travels at the same speed, whether it's this way or this way, you won't get an interference pattern. Well, we don't get an interference pattern. Okay? We don't develop an interference pattern. We don't see light changing its speed, going in one direction or the other. It travels at a constant speed. So all we can conclude from Michelson and Morley is that the speed of light is constant regardless of what frame, and that it doesn't necessarily travel through a medium. Okay? Doesn't seem like a big deal at that point, or it doesn't seem like a big deal to you. Let me correct myself, because it was a big deal at that time. Still is a big deal. But it sets up the foundations for Einstein in 1915 to come up with his theory of special relativity. Okay? It's a big deal. Now, moving on, the Curies. The Curies making their big discovery that eventually kills them. Radiation, or radioactivity. The Curies coined the phrase radioactivity by finding radium and soot black, or I can't remember the name of it. But it's a waste product, I do believe. They find radium in there, and radium is highly radioactive. As a matter of fact, they take this material and they basically distill it, and they separate all the elements out of that material, and they find two new elements, and one of them is radium. And we continued for a long time after the Curies, after their death, to use radium in things like watch in the hand dials on, or the hands on watches, painting things that we needed to glow in the dark. You know, we use that radium to do that, and it's toxic. Not toxic. It's radioactive. It'll kill you. So, 1897, you have the beginning of nuclear physics. We have the discussion of radioactivity. These particles are decaying, and we're running into these strange effects, radium being one of them. So that's 1897, nuclear physics. Okay? Thomson, my boy Thomson. So Thomson's kind of the kicking, the not the scapegoat, but he's kind of he gets blamed for a lot of things. Okay? Thomson in 1897 wins the Nobel Prize for his experiment. His experiment in 1897 was to determine the mass to charge ratio of an electron. Okay? He develops a way in which, much like a mass spec, where you bake electrons off and you send them through a potential, a voltage. You accelerate those electrons and you put them inside of a magnetic field, and those electrons circle around. That radial value will give you an idea of the mass to charge ratio. So in 1897, Thomson wins the Nobel Prize for this experiment, which is kind of funny, as I've performed this experiment in college, not even knowing the origins of it, which is kind of a shame, actually. So Thomson wins the Nobel Prize for that. From this model, he comes up with what's known as the plum pudding model. Thomson's model on plum pudding says that, oh, look, we found these little chunks of charge called an electron floating around in the atom. So it's a small, small chunk. Excuse me. It's a small, small chunk of the total mass of that atom. So the rest of the mass must be this kind of gelatinous-like blob material that we glue together. So you get one lone, or you get an electron in there, and then the rest of it is just kind of an ooze, okay, with a positive charge. So that's the plum pudding model. You get this pudding that's got chunks in it, and these chunks are electrons. And because they're separate from this ooze, we can liberate them. And that's what Thomson believed at that time. Obviously, that's incorrect, but that's his model. Okay, and that's in 1897. Okay, next, Planck. Oh, probably one of the most important discoveries of all time. Well, not of all time, but of modern physics. Planck discovers the Planck constant using blackbody radiation. Now, what that does is that it gives validity to a lot of other things, that energy is discrete. You start coming up with the word quantum, quanta, at that point, where we're talking about this H value that floats around everywhere when talking about quantum mechanics. It's to describe energy in small packets. That's what quantum means. It means energy in small packets. So Planck sets up the foundation for quantum mechanics in 1900. He's the grandfather of the whole modern physics, whole quantum mechanics thing. Okay, his Planck constant ends up revolutionizing the way in which we look at the universe. Okay, Rutherford, Geiger, and Marsden. Probably another critical experiment. So we've got Michelson and Morley talking about sending light around a box, basically, to see if it interferes with itself, and we discover that light doesn't need a medium. We have Thomson, who discovers a charge to mass ratio. He discovers the electron, if you will. Okay? And then you have Rutherford, Geiger, and Marsden. Wilson's experiment for the test. So what are we talking about? A total of... So their experiment is the gold foil experiment. So you take a sheet of gold, you flatten it out as much as you can, okay? So it's only a few atoms thick, and you fire alpha particles through that gold. Well, if this is the model of the atom, then this is just kind of a thick, or not a thick, a blob of this material with small chunks in it. These chunks are so small compared to the overall mass and volume that the odds are these alpha particles will just cut through this weak, positively charged goo. It'll just go right through it. So the idea is these alpha particles go through that material and continue with minor, if any, deflections. Okay? Cool? But what we find instead is that most particles go through like we expected, but every once in a while you get these massive deflections as it's going through those particles. Okay? So what that does for Rutherford, Geiger, and Marsden, and mind you, the experiment is called the Geiger-Marsden experiment. Rutherford is the man who supports it. He's the man who pays for everything, pretty much. Rutherford's an interesting person. What we have to conclude from that is that this is not a valid model for the atom. Rutherford comes in, gets that data, and concludes different than what we expected. And we get Rutherford's planetary model for the atom, which, I don't know if I'm enough to write this. Yeah. Rutherford, you have the sun, or in this case, the center, and then you have an electron orbiting that nucleus, much in the same way as planets orbit the sun. Okay? That's a little bit easier one to see, but it's still not all that great. Okay? But Rutherford's model says that these particles will behave exactly like planets. So if you take away a little bit of energy, they just drop into a different orbit. Okay? They just drop into this different orbit. They behave exactly like the classical model of the universe. If you look at planetary orbits are not discrete values. They're continuous values. They can be anywhere. So you got these orbiting electrons, and these orbiting electrons, if they're given up a little bit of energy, just simply degrade into a smaller orbit and just keep circling. The problem with that is spectroscopy. Spectroscopy hides that value. Okay? So I'm going to end it there on this one. I'm going to go ahead and talk about some of the other things that happened after 1909. But you've got Michelson, you've got Thomson, you've got Rutherford, you've got Curie, and you've got Planck. Some of the really big events that happened in the late 1800s to the very early 1900s that affect quantum mechanics, or modern physics, I should say.